Welcome to Learn with us. This is the second lecture of Basic Electronics.
Before starting this lecture, first we will have a quick review of what you have learned in your previous lecture. In your last lecture, you understood the difference between electrical and electronic circuits. You also studied what are free and valence electrons. In your previous lecture, you also studied about the materials that are used in electronics, and you also understood their band models. In your previous lecture, you also studied comparison of semiconductor atom to a conductor atom. Now, what are the learning objectives of this lecture? In this lecture, you will study what are intrinsic semiconductors. You will understand current in semiconductors. In this lecture, you will also study about extrinsic semiconductors, and you will also understand what is p-n junction. What are intrinsic semiconductors? A perfect semiconductor with no impurity is intrinsic in nature. Germanium and silicon are the most common types of intrinsic semiconductors. They both are tetravalent. It means they have 4 valence electrons in their valence shell. Now, look at this figure. The valence electrons in germanium are in the 4th shell, while the valence electrons in silicon are in the 3rd shell, that is, closer to the nucleus. This means that the germanium valence electrons are at higher energy levels than those in silicon, and therefore these valence electrons in germanium require a smaller amount of additional energy to escape from the atom. This property makes germanium more unstable at high temperatures. It results in excessive reverse current. This is why silicon is a more widely used semiconductive material. It is used in diodes, transistors, integrated circuits, and other semiconductor devices. Now we will understand crystal structure of silicon. Silicon atoms are arranged in a definite symmetrical pattern, making them a crystalline solid structure. A crystal of pure silica, that is, silicon dioxide or glass, is generally said to be an intrinsic crystal. It means it has no impurities and therefore it has no free electrons. Now, look at this figure. It shows how each silicon atom positions itself with 4 adjacent silicon atoms to form a silicon crystal. A silicon atom with its 4 valence electrons shares an electron with each of its 4 neighbors. This sharing of valence electrons produces the covalent bonds that hold these atoms together. These pink signs represent the shared valence electrons. Covalent bonding in an intrinsic silicon crystal is shown in this figure. Now we will understand current in intrinsic semiconductors. The way a material conducts electrical current is important in understanding how electronic devices operate. You can't really understand the operation of a device such as diode or transistor without knowing something about current in semiconductors. An intrinsic or pure semiconductor has two types of charge carriers. First is electrons that are negatively charged, and second is holes that are positively charged. At room temperature, pure semiconductor has sufficient heat or thermal energy for some valence electrons to jump the gap from the valence band into the conduction band, becoming free electrons. These free electrons are also called conduction electrons. Now, look at this figure. When an electron jumps from the valence band to the conduction band, a vacancy is left in the valence band at the electron position within the crystal. This vacancy is called a hole. For every electron raised to the conduction band by external energy, there is one hole left in the valence band. Both the free electrons in the conduction band and holes in the valence band are generated at the same time. These free electrons carry the negative charge or electric current from one place to another in the conduction band, whereas these holes or vacancies, they carry the positive charge or electric current from one place to another in the valence band. In intrinsic semiconductors, the total number of negative charge carriers or free electrons is equal to the total number of positive charge carriers or holes or vacancy. This is called an electron hole pair, as you can see here. Now, what is recombination? Recombination occurs when a conduction band free electron loses its energy and falls back into a hole in the valence band. This figure illustrates electron hole pairs in a silicon crystal. As you can see here, free electrons are being generated continuously, while some of these free electrons recombine with holes, as you can see here. So this is what we call generation, and this is recombination of carriers. Now we will understand electron and hole current. There are two types of current produced in a pure or intrinsic semiconductor. First is electron current and second is hole current. When the voltage is applied to a pure or intrinsic semiconductor, the free electrons move towards the positive terminal of a battery and holes move towards the negative terminal of a battery. We know that electrons are the negatively charged particles and holes are the positively charged particles. Since like charges repel each other and unlike charges attract each other, therefore the electrons or negatively charged particles are attracted towards the positive terminal of a battery and holes or positively charged particles are attracted towards the negative terminal of a battery. This movement of free electrons in the conduction band is one type of current in a semiconductive material, and it is called electron current. Another type of current occurs in the valence band where the holes created by the free electrons exist. It is called hole current, in which the hole has moved from one place to another in the crystal structure. Although current in the valence band is produced by valence electrons, it is called hole current to distinguish it from electron current in the conduction band. Now, look at this figure. It illustrates generation of electron current in intrinsic silicon. This electron current is produced by the movement of thermally generated free electrons. As you can see, these free electrons, being negatively charged particles, are attracted towards the positive terminal of a battery. Now, look at this figure. This figure illustrates mechanism of hole current generation. Look at these steps. In first step, a free electron leaves a hole in the valence shell. In second step, a valence electron moves into this first hole and leaves a second hole behind. In third step, a valence electron moves into this second hole and leaves behind a third hole. It means when a valence electron moves from left to right to fill a hole, it leaves another hole behind. On the other hand, the hole has effectively moved from right to left. These gray arrows indicate effective movement of a hole. So, it means electrons are moving from left to right and holes are moving from right to left. This is how hole current is generated in intrinsic silicon. Now we will talk about extrinsic semiconductors. Since semiconductors are generally poor conductors, their conductivity can be drastically increased by the controlled addition of impurities to the intrinsic or pure semiconductive material. It means extrinsic semiconductors have impurities. Doping is a phenomena in which addition of external impurities to the host atom takes place. These host atoms can be silicon or germanium. This doping alters the electrical or resistive properties of the material. It increases the number of current carriers, that is, electrons or holes. These doped semiconductors are those in which one kind of carrier predominates in a controlled way. An extrinsic semiconductor can be further classified into two types. First is N-type semiconductor and second is P-type semiconductor. Now we will talk about N-type semiconductor. In N-type semiconductor, pentavalent impurity atoms are added to increase the number of conduction band electrons in intrinsic host atom. These pentavalent impurity atoms are atoms with 5 valence electrons such as arsenic, phosphorus, antimony, etc. These atoms introduce free electrons in the host atom, the number of free electrons depends on the amount of impurity added to the intrinsic host atom. A small addition of impurity generates millions of free electrons. Therefore, such impurity is also known as donor impurity. Since the pentavalent atom gives up an electron, it is often called a donor atom. This type of doping is also called pentavalent doping. In N-type semiconductors, electrons are the majority carriers and holes are the minority carriers. It is measured in electrons per cubic centimeter. Now, look at this figure. We know that there are 5 valence electrons in the phosphorus atom and 4 valence electrons in the silicon atom. So, when this phosphorus atom is added to pure silicon, then 4 out of 5 valence electrons of this phosphorus atom make covalent bonds with neighboring silicon atoms, as you can see here. As a result, the 5th valence electron of this phosphorus atom becomes free. It becomes a conduction electron. The number of conduction electrons can be carefully controlled by the number of impurity atoms added to the pure silicon. Now we will talk about p-type semiconductor. In p-type semiconductor, trivalent impurity atoms are added to increase the number of holes in intrinsic host atom. These trivalent impurity atoms are atoms with 3 valence electrons such as boron, indium and gallium. These atoms introduce shortage of electrons, that is holes, in the host atom. The number of holes can be carefully controlled by the number of trivalent impurity atoms added to the host atom. Such impurity is known as acceptor impurity. Since the trivalent atom can take an electron, it is also known as an acceptor atom. This type of doping is also called trivalent doping. In p-type semiconductors, electrons are the minority carriers and holes are the majority carriers. It is measured in holes per cubic centimeter. Now, look at this figure. We know that there are 3 valence electrons in boron atom and 4 valence electrons in silicon atom. So, when this boron atom is added to pure silicon, 3 valence electrons of this boron atom make covalent bonds with neighboring silicon atoms, as you can see here, and lack of one electron gives rise to a hole in this p-type semiconductor. Now, this is the summary of what we have studied so far. We have studied that there are 3 groups of materials that are used in electronics. First group is conductors, second group is semiconductors, and third group is insulators. The main difference between all these groups rely on their level of conductivity. Conductors conduct electrical current. Insulators do not conduct electrical currents, and semiconductors are between conductors and insulators. Now, when we talk about semiconductors, there are two types of semiconductors: intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductors are pure form of semiconductors with no impurities, whereas extrinsic semiconductors have impurities. These extrinsic semiconductors are further divided into two types: N-type semiconductor and P-type semiconductor. In N-type semiconductor, pentavalent impurity is added to increase the number of free electrons in the host atom, whereas in P-type semiconductors, trivalent impurity is added to increase the number of holes in the host atom. In N-type semiconductors, electrons are the majority carriers and holes are the minority carriers, whereas in P-type semiconductors, holes are the majority carriers and electrons are the minority carriers. Now, what is a p-n junction? If a piece of intrinsic semiconductor is doped so that one part is n-type and the other part is p-type, then a p-n junction is formed at the boundary between the two regions. This p-n junction is a basic building block for many electronic devices. Now, look at this figure. This is the basic silicon structure at the instant of junction formation, showing the majority and minority carriers. This is N region, where the majority carriers are free electrons. This is P region, where the majority carriers are holes. And this is p-n junction, which is formed at the boundary between p and n regions. These free electrons in the n region near this p-n junction begin to diffuse across the junction and fall into the holes near the p-n junction in p region. Now we will understand what is the depletion region. When the p-n junction is formed, the n region loses free electrons as they diffuse across the junction. This creates a layer of positive charges, that is, pentavalent ions near the junction. As the electrons move across the junction, the p region loses holes as the electrons and holes combine. This creates a layer of negative charges, that is, trivalent ions near the junction. These two layers of positive and negative charges form the depletion region. Now, look at this figure. For every electron that diffuses across the junction and combines with a hole, a positive charge is created in the n region and a negative charge is created in the p region, as you can see here. As these free electrons continue to diffuse across the junction, more and more positive and negative charges are created near the p-n junction, forming the depletion region. These blue arrows between the positive and negative layers represent the electric field. As you can see, it is from N region to p region. The forces between the opposite charges are forming this electric field. Now, what is the barrier potential? A point is reached where the total negative charge in the depletion region repels any further diffusion of electrons, that is, negatively charged particles into the p region, because we know that like charges repel each other. As a result, the diffusion stops. Now, the depletion region acts as a barrier. The electric field is a barrier to the free electrons in the n region, and energy must be expended to move an electron through the electric field. So, the amount of voltage required to move electrons through the electric field is the potential difference of the electric field across the depletion region. This potential difference is called the barrier potential. It is expressed in volts. The barrier potential of a p-n junction depends on several factors, including the type of semiconductive material, the amount of doping, and the temperature. The typical barrier potential is approximately 0.7 volts for silicon and 0.3 volts for germanium. Now we will understand the current equation. It is the equation of current where IDIF is I diffusion, which is the current caused by electron diffusion opposite from direction of electron. It means it is from P to N. In addition to diffusion current, there is another current which is drift current. We know that minority charge carriers also exist in both regions, that is, holes in N region and free electrons in P region. So, holes in N region diffuse through the edge of depletion region. Similarly, electrons in p region diffuse through depletion region. Both of these charge carriers experience electric field in the depletion region, which sweeps holes into the p region and electrons into the n region. These two phenomena create drift current. It is also called reverse current. It is from N to P. Now we will look at the energy diagram of p-n junction and depletion region. Look at this figure. As you can see, the conduction band and the valence band in the n region are at lower energy levels as compared to the conduction band and the valence band in the p region. The free electrons in the n region that occupy the upper part of the conduction band in terms of their energy can easily diffuse across the junction. This is the junction. It means they do not have to gain additional energy and they temporarily become free electrons in the lower part of the conduction band in p region. After crossing the junction, these electrons quickly lose their energy and they fall into the holes in the p region valence band as shown. As this diffusion of free electrons continues. The depletion region begins to form. As a result, the energy level of the N region conduction band decreases. This decrease in the energy level is due to the loss of higher energy electrons that have diffused across the junction to the P region. Here I am showing an animation which is explaining the energy diagram of PN junction and depletion region that I have discussed in the previous slide. So have a look at this animation. When electrons diffuse across the junction, they fall into the hole, and as a result, depletion region is formed. Now look at it again. The conduction band in N region is at lower energy level as compared to conduction band in P region. So when these electrons diffuse across the junction and enter P region, they lose their energy and fall into holes in valence band in P region. As a result, depletion region is formed. Now look at it again to make it more clear. When these free electrons diffuse across the junction and they enter the conduction band in P region, they lose their energy and fall into holes in the valence band in P region. As a result, depletion region is formed. Now, here is your class task. Why the valence and conduction bands in an N-type material are at slightly lower energy levels than the valence and conduction bands in a P-type material. Take 2 minutes to complete this task. That's all for today. Let's have a quick recap. In this lecture, you understood what are intrinsic semiconductors. You also studied about currents in intrinsic semiconductors. In this lecture, you also understood what are extrinsic semiconductors and what are the different types of extrinsic semiconductors. In this lecture, you also understood what is PN junction and what is depletion region.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.